Hello, friends of Sudoku, and welcome to an expert level Sudoku. It's not me saying so, it just says so on the paper that I'm looking at. So, without further, this really is an expert Sudoku or if it is a misnomer. There aren't that many givens here, so let's see how it goes. I do see a couple of nines blocking down and a 1 and a 9 blocking over, so a 9 must go here. There's also a couple of fives blocking like so and one blocking over, and therefore this must be a 5. I know that one of these squares must be a 7 because the 7 blocks down here and this 7 blocks over, so one of these is going to be a 7 eventually, and therefore one of these must be a 7. So I'm already beginning to look for a 7 in these squares here. There's none to be found yet. What I can see though for this row is that we have a 2, 9 here and we have a 2, 9 here. So the 2s and the 9s are taken care of for row 7 and row 9. We need a 2 and a 9 for row 8. And clearly they can't go anywhere here. So they have to go here. Uh, Since therefore neither of these squares can be a 6, and we got a couple of 6s blocking down like so, it follows that this square must be a 6. We're going to need a 4 for the bottom row. This 4 blocks over here and this 4 blocks down here. So one of these is going to be a 4 and therefore one of these two squares must be a 4. I'm noticing that a 3, 4, 5, 6 and a 7 are required for this row, and there's a 4, 6 and a 7 here, so this is a 3 or a 5. I can also see that the 3 blocks down here and the 3 blocks over, so one of these is a 3 and therefore one of these must be a 3. It's all just adding to the information that I'm gathering that I may make use of later on. We only have 3 givens in column 2, and it's not easy to spot, but there is a singleton here. But if you look at the ones, the 1 can't go here, and there's a 1 blocking these 3 squares. There's a 1 blocking over here. So therefore, this is a 1. Now we need to find a 2, 3, 7, and a 9 to complete row 6. There's a 2, 9, 7 here blocking this square. So this must be a 3. We got a couple of 3s blocking up now and 1 blocking over. So the square here is a 3. But we were talking about this row here, weren't we? We still need to find a 2, 7, 9, and a 4 for these squares here. Let's see, there's a 7 and a 9 here, so and a 2 must go over here somewhere. We know that one of these must be a 2, so no, it's not quite obvious yet where those will have to go. But we got ourselves a 3. These squares must be a 2, 6, and a 4. All we know is that this must be a 4 or a 6. But that's not quite enough. But this is a very pretty pattern. Look at the 3, 5, 9 here and the 3, 5, 9 here and the 3, 5, 9 here. I think it's probably not by design, but it's quite nice. I'm doing a little calculation here. I can see the 7 blocks here, and we can't have a 7 in these two squares, so one of these must be a 7. And I also know that a 2 must go in one of these two squares. So I'm looking at this square now. What can it be? It cannot be a 2, 3, 4, 5. It could be a 6, but not a 7. It could be an 8, but not a 9. So this is a 6 or an 8. We also have a 6 and an 8 here, by the way. I'm not sure if it means anything, but it's something I like to keep track of. One of these now must be a 7, of course, since one of these is a 7. I'm eager again to show how I do pencil marks. So why don't we use this puzzle as an example? I'm not saying I couldn't make headway now without pencil marks, but it does look a little troublesome. So why not just play with the pencil marks and see what happens? Let's first try the Snyder notation. The Snyder notation, as we have mentioned before, stipulates that if a digit can go in one 3 by 3 box exactly twice, then we are allowed to enter the pencil mark. So for the ones, for example, we can see that a 1 can go here and here. So let's just enter a 1 like so. We also see the 1 blocking over here and the 1 blocking down here. So one of these is going to be a 1. These two ones block up and one blocks over. So these two squares can be 1 candidates. In this box here, we have only these two squares blocked by 1s. So these 3 squares can contain 1s, but Snyder notation says we shouldn't enter anything here then. So on to the 2s. I know that these 2 can be 2s. And I know that these 2 can be 2s because we said so. We got a couple of 2s blocking up here like so. Therefore, these 2 are also candidates for a 2. And that's as far as we can take the 2s. The 3s then, we got a couple of 3s blocking over. And therefore, a 3 will go here or here. The 3 blocks down. This blocks over. One of these is a 3. One of these is a 3. And therefore, one of these is going to be a 3. That's it for the 3s. Let's look at the 4s. One of these must be a 4. One of these must be a 4. This 4 blocks over. This blocks down. One of these is a 4. And therefore, one of these must be a 4. 5s now. We got a couple of 5 candidates here. And I think that's it for the 5s. Yes. So 6s. We only have a couple of 6. Well, we have 3 6s. But they're not really doing much for, yes, this 6 blocks over, so these 2 squares are candidates for 6, but that is it for the 6s. 7s, then we know that one of these is a 7, and we know that one of these is a 7. And now we have the 7 blocking over here and the 7 blocking down. One of these must be a 7. And I think that's it for the 7s. 8s now. For the 8s, we can't do anything, I think, because they are spread over like this. 9s. 9 is also not very obvious because they are spread like this in one shoot. So there's nothing we can do about this. So what does this tell us about the possibilities for the next digit? To be frank, I don't see much here because these pencil marks are spread all over the place. They are following the Snyder notation, but we do have a 174 grouping here, but they are spread over 4 digits, and therefore they can't really be taken as a triple. Let's look up here. We have a 1-4 here, 1-4-6 here. We still need a 2 to complete the column. There's a 4 and a 6 here, so this is a 1 or a 2. The problem is that a 1 also could potentially go in these squares here. So we would have 4. So we would have 3 squares for a 1. And as usual, I have to say with more difficult puzzles, Snyder notation doesn't help me much. So I will now pause the video and remove all the Snyder notation pencil marks and we'll start over. So I'm back. And now I want to introduce you, if you haven't seen my previous videos before, to my way of doing pencil marking, which I find more productive with complex puzzles. Not easy puzzles, mind you. Easy puzzles can be quite easily solved using Snyder notation alone, but the Snyder notation usually fails me for the more difficult puzzles. So what I like to do is I like to enter values into cells that can take exactly 2 values by value cells. And that's all. Let's try that and see what happens. I will pause the video again and I will enter all the values that are possible for this grid. So here are the digits that I have found so far. There are more digits and we'll get to them in short order. The only tricky part was to find this remote pair here, because if you just do a simple count here and here, you can see that the only digits available as candidates for these 2 squares are the 6 and the 8. And that gives this result that these 4 squares now must be the difference between 1 through 9 and the givens. And that is a 1, 2, 5, and a 9. So if we look at this square here, it must be a 1 or a 2, because we already have a 5 and a 9 in this box, and we already have a 1 and a 2 here. So this is in fact a 1-2 pair, and that makes this square here a 4 and a 6, because we only have 2 squares left in the column. And since we have a 6 down here that blocks this square, we know that this must be a 4. And therefore this must be a 6. Snyder notation hadn't found it. Snyder notation wouldn't have found this. But this way of markup finds these pairs quite easily. I'm not saying I couldn't have found this just using mental powers if I'd had the time or probably the luck. But this is one sure way of improving your chances of finding digits. And see what happened when we found the 6 here. This by value cell that was a 2 or a 6 before, since we have taken away the 6 now, we know for sure that this must be a 2. And therefore we know for sure that this must be a 5. So in this way, this kind of markup works exactly the same as a Snyder notation. As soon as you take away one possibility from a square, you will know precisely where the other digit is going to go. So we can see how far we can take it from here without further pencil marks. I like to keep my grids tidy. And by that, I mean not clutter it up with a lot of pencil marks all over the place. And I'm certainly never going to allow myself to input all possible pencil marks for the entire grids, because that will obscure the final result. So we got a 1 and a 2 here. We got a 6, 8 here. What's the last digit missing? That's right. It's a 7. So a 7 we know will have to go here, and a 7 will have to go here because we established that fact earlier on. Now that we found these 2 here, we know that this square must be a 2. These 4 squares now must be a 3, 5, 7, and a 4. We know that a 5 will have to go in one of these 2 squares. And we know that the 7 and a 4 blocks here. So a 4 will have to go over here. We also know that the 7 blocks over here and down here. So this is in fact a 7. And therefore one of these now must be a 7 and the other must be a 9. I will not bother inputting the 7, 9 pencil marks here because it's a waste of time, frankly, and we can easily remember these two squares being a 7 and a 9, right? The 5 blocking here, the only square available now in this row for a 5 is exactly here. So we will just enter the 5 here and make a note that these have to be a 3 and a 9. So if these are 3s and 9s, these must be, of course, a 1 and a 6. These must be a 3 or a 4, or rather a 3 and a 4. And we have a 3 blocking down here. So we know that the 4 must go here and the 3 here. And we shouldn't fall into the trap of mindlessly thinking that we have 3s blocking over here, and therefore the 3 blocking down here, and the 3 blocking down here, and the 3 blocking over here, making this a 3. It may very well be a 3, but look here, we are not saying that one of these must be a 3. One could be a 7 and the other could be an 8. So we're not going to do that. The reason I'm saying it is that I have been prone to doing that earlier, before I got more experience at solving these grids. I'm just giving you a friendly warning not to do that, because you will end up in a world of hurt if you make a mistake and you have to start over. Starting over is never fun. Let me tell you, I've done that many times. We do remember the 1, the 9, and the 2s here from earlier, don't we? The 9, 2, the 9, 2, the 9, 2. Now that we have this 2 here, we know that the 9 must go here and the 2 must go here. And the 9 blocking up here now makes this a 3 and this a 9. We got a 9 now blocking up, and blocking up, I should say, and 1 blocking over. So this square's got to be a 9. These two 9s are blocking over, and this is blocking up. So a 9 must go here as well. Now this 9 blocks down. We know that these were a 7, 9, right? So we can enter a 7 here and a 9 here without even thinking about it. The 6 blocks here, so one of these must be a 6. We also need to find a 4 for this row here. And we know from earlier that one of these had to be a 4. We now found the 4, and we know that one of these therefore had to be a 4. Since this 4 now blocks here, there's only one available square for 4 now in the row, and it has to go here. Remember how I just said that a 6 must go in one of these two squares? Because the 6 blocks up here and the 6 blocks down here. Therefore, this now must be a 6. And that puts a 6 in this square, and therefore in this. These two squares now must be a 8 and a 7, and therefore this square can only be a 1. We got a couple of 1s blocking over like so, and a 1 blocking down like so. So this is a 1. Now we see a single 8 up here. The single 8 means that there was another digit in there before, and something we did took away that candidate, left only the 8. So chances are that this square must be an 8, but let's do a simple count. A 1, 2, 3, 4, 5, 6, 7, and a 9 cannot go here. So it is an 8, and therefore one of these squares must be an 8. The reason we can say that with certainty is that remember how these two squares were 6s and 8s. So as soon as we took away this square and gave it to a 6, this square automatically had to become an 8. Now we have two corner squares. One must be a 3 and the other must be a 5. We have a 3 that blocks this square, and therefore this must be the 5 and this must be the 3. Remember our earlier discussion about not assuming that this square is a 3. Now it's proven to be a 3, but we couldn't have known that before. That's why I had to wait until I was sure. Now I'm sure. 3, 7, and 8 for these squares here now. There's a 3 here blocking. So this is a 7 or an 8. We know that the two other squares here must be a 5. So actually we have a 5, 7, 8 for these three squares, and we got an 8 and a 5 blocking down. So this has got to be a 7. These are now 5 and 8s. Therefore, this is a 5 and 8 too. I mean, we only have two squares left, and they have to be a 5 and an 8. And the solution is simple because this 5 blocks this square, making it an 8, making this a 5, making this an 8. This must be a 3, and this must be a 7. One square to go here, and that is a 7. Two squares to go here, namely an 8, which must go here because it's the last missing digit in the column, and a 5. The 5 blocking up, and two 5s blocking over, making this a 5. These two squares now must be a 4 and an 8. I can't resolve them. What about these? They have to be a 1, 2, and a 3. We got a couple of 3s blocking over, so this is a 3, and we got a 1 blocking over, so this is a 2, and therefore this is a 1. And that resolves the 1, 2 pair we had here. This is now a 1, and this is 2, making this a 2, of course. And these are still an 8 and a 7. Let's see about this square here. It must be a 5 or a 7. It must be a 6 or a 7 to complete this column here. And there's a 7 blocking here. So this must be the 6 and this must be the 7, giving me the 7 here and the 8 here, like so. And therefore, this is an 8 and this is a 4, making this a 4. This square now must be a 6. And this last square is going to be a 1. We solved this expert puzzle as well. It was considerably easier to solve using this kind of markup than if we had continued to use Snyder. And I'm not advocating that you should never use Snyder, because you should use whatever works for you, not what works for me. I'm just opening up the possibility to use another form of notation for difficult puzzles. As I said before, I think Snyder is very good for easy puzzles, but not, or medium, or maybe even hard puzzles. But for more advanced puzzles, I don't think that Snyder does enough for me personally. So this is just how I do it, and you're welcome, of course, to do whatever is best for you. I hope that you did enjoy it, though, and that you followed through to the end. And I thank you for watching. Goodbye for now.